Hey, this is Dr. B, and let's take a look at chemical equilibrium. This is really a case of where we're looking at the reversibility of a chemical reaction. And this runner on a treadmill is an apt analogy. Chemical reactions are often reversible. For example, if A plus B is forming C plus D, why can't C plus D reverse itself and form A plus B? In fact, it can. So chemical equilibrium will eventually occur when you get to the point where the forward rate, like that person running there, is equal to the reverse rate, which is the rate of the treadmill going in the opposite direction. That's my visual for chemical equilibrium, forward and backward, and when it's going at the same rate, well, it looks like the reaction is stopped, but whatever you do, don't choose that answer on a multiple choice test. The reaction has not stopped. Things are still reacting, just at equal and opposite rates. Scientists have defined this mathematically using the following formula. The equilibrium constant K, where if it's a small unitless number, it means a relatively lousy equilibrium where we're going more backwards than we are forwards, if you will. Or big number means you've got a nice equilibrium and it's going to nearly to completion, for example, on its own, which I think of as a good thing. And we define it as the concentration of the products, which in this case is C and D, over the reactants, A and B. And in this case, notice this is a big difference from rates. Those coefficients in the balanced chemical equation do become exponents. So make a note. Yes for equilibrium, no for rates. And in fact, you may recall that for rates, we ignore the products. It's just equal to some constant. The rate is equal to some constant times the concentration of the reactants, but raised to some power that's determined experimentally. Here it's all laid out for you, so there's a big difference between how we set those up. If it's low, I think of that as a bad thing. If it's high, I think of it as a good thing. I think that's true if you're really trying to get to those products and as much of them as you can. Now we do want to consider only that which can reverse itself. And if something precipitates, for example, as a liquid or a solid, it's gone from that flask in terms of being able to mix intimately and to reverse itself. So watch out for those liquids and solids. We can also consider if you're at equilibrium, if you're beyond it, or if you're not there yet. The actual ratio of products to reactants at any given time, regardless of whether you're at equilibrium or not, they just call that Q. And sometimes it's going to be below K, meaning you're not there yet. So the reaction will proceed to the right? It'll go forward. If you actually measure the concentrations of products and reactants at a given time and you're beyond K, well, that's overshot it a bit, and the reaction will shift to the left until it matches those equilibrium concentrations. For me, that gives you a good idea of how things will adjust to meet equilibrium. So let's practice writing some equilibrium expressions. Here's one that's designed to be straightforward. KEQ is going to be equal to the products, the concentrations of the products. There's only one, but it's that coefficient becomes an exponent, so don't forget to square it, over H2 times I2, and there it is. For this one of iron 2 oxide with carbon monoxide, two of these are solids, so slash, and it'll simply be equal to the concentration of the carbon dioxide over the carbon monoxide. One small note, since in these cases we're talking about gases, we could use pressures because are not partial pressures relative concentrations? They are, so they can be substituted in just fine. Here's one where we give you not only the balanced chemical equation, but enough data to solve a problem. We know what the concentration of sulfur is. We know what the concentration of hydrogen sulfide is. We know what the equilibrium constant is. So when you set up the expression, you'll have everything except the hydrogen concentration. If you want to pause this and solve it, go ahead. Nothing gets omitted. And we have the concentration of the hydrogen times the sulfur. There's our two products. Don't forget to square that. Over the H2S concentration, which also must be squared. We'll have everything except hydrogen. Good. So you can turn this stuff here into a number. You can solve for H2 squared. and then simply take the square root, and you'll find that the concentration of hydrogen in this problem is 0.0377 moles per liter. This is an introduction to chemical equilibrium.